All right, welcome everybody to the online edition of Control Systems EE 480. So today we're going to be continuing with our lecture talking about partial fraction expansion. So this should be a review for most people, just trying to break off the rust, go through this process, and then be prepared for the type of work, type of math we're going to be doing in this class. So as we mentioned last time, there's really three examples we have, three different cases for doing a partial fraction expansion. One is the case where we have real and distinct roots. The other case is where we have repeated roots. And the last case is where we have complex roots. And these three cases we treat differently. So each one we're going to handle slightly differently in the way that we do the math to do the partial fraction expansion. So let's start with an example of real and distinct roots, a real and distinct roots example. So for this we're going to be using the function f of s is equal to 2 divided by s plus 1, s plus 2. So clearly here we're going to have two real distinct roots. The roots in this case are going to be -1 and -2. So to do the partial fraction expansion on this, the first thing we're going to do is we're going to assume a form of the solution to this. So the form of the solution is going to be k1 over s plus 1 plus k2 over s plus 2. So we're assuming essentially that this term can be represented as some fraction residue k1 over s plus 1 plus k2 over s plus 2. So after we make this assumption, the next thing we have to do is solve for these coefficients k1 and k2. And the way we do that is fairly straightforward. We're going to manipulate this equation such that we're going to get rid of one of these terms, leaving just k1. Then we're going to choose a value for s that makes it easiest for us to solve for this unknown. And then we're going to solve for that unknown. So the first thing we're going to do is, if we're going to solve for k1, we're going to want to multiply both sides by s plus 1. So then what do we get? The s plus 1s here are going to cancel. I don't want to draw it, but they're going to cancel. So we're going to be left with just a k1 here. And then this guy, we have to get rid of that k2, because we have one equation we're trying to solve for this one unknown k1. So to get rid of the k2, we're going to choose a value of s that wipes it out. So in this case, to make a 0 in the numerator, if we choose s equals to -1, then that'll wipe out this term. So we'll have, if s is equal to -1, this term goes to 0. This term is still k1 because of this cancellation. And we have, this cancels out here too. So we're going to have 2 divided by -1 plus 2. That's going to be k1 equals 2 divided by -1 plus 2. That's going to equal 2. So to solve for k2, we're going to repeat this process, but we are going to multiply, in this case, by s plus 2. Okay, so now I can actually, because this is the last thing I'm going to do with this equation, I can wipe those out, wipe those out. Now we have to choose a value of s to get rid of this k1 term, so we get to pick s is equal to -2 in this case. So if s is equal to -2, this guy goes to 0. And then over here we have 2 divided by -2 plus 1, that's going to be 2 divided by -1. So we have k2 equals -2. So that is the process we go through for partial fraction expansion with real and distinct roots. So now let's, so if we want to continue this, right? So we know these coefficients now. So that means we can rewrite our expression as f of s is equal to, we have 2 over s plus 2. And then we have plus -2 over, 2 over s plus 1. Plus -2 over s plus 2. And we can do, so we can take the inverse Laplace transform for each one of these two terms, and we get f of t is equal to, this is going to be 2e to the -1t plus negative 2e to the negative 2t. And again, we can find these inverse Laplace transforms by looking at any Laplace table. So. Okay. The next example is the example for repeated roots. So let's go back. We're going to do another equation example here. So we will do f of s is equal to 2 over s plus 1 times s plus 2 squared. So clearly here we have a repeated root of negative 2. We have a root of negative 1 and a repeated root of negative 2. So how do we analyze this situation? Well, for the non-repeated root, we can solve it pretty much the same way we did in the case of the real and distinct roots. So first thing, before we get too far ahead of ourselves, we're going to write this as, we're going to assume the form for repeated roots of k1 over s plus 1 plus k2 over s plus 2 squared plus k3 over s plus 2. So we have to, so for the repeated root case, the assumed form is 1 repeated root residue, and we can manage with this, and then 1 non-repeated root residue term. Okay, so solving for k1 is fairly straightforward. So to solve for k1, we're just going to multiply both sides of this expression, of this equation, by s plus 1. Okay, so now, again, I want to leave this equation up here. So these guys cancel out, so all we have left here is a k1. k2 and k3, these are both now multiplied by s plus 1. So how are we going to get rid of those to solve for k1? We're going to choose s is equal to negative 1. So if s is equal to negative 1, the numerator is 0, numerator is 0. These guys both get wiped out. So all that's left on this side of the equation is a k1 at s is equal to negative 1. Now over here, these terms get wiped out, so what we're left with is a 2 divided by negative 1 plus 2 squared. That's going to be 2 divided by 1, so k1 is equal to 2 divided by 1. So k1 is simply equal to 2. We're getting used to a lot of 2's as our answer. That's just coincidence here. So to solve for k2, we can do a similar process. To solve for k2, we are going to multiply both sides of the equation by s plus 2 squared. So solve for k2, we're going to do s plus 2 squared okay. So s plus 2 squared wipes out the terms here. All that's left here is now a k2. And now this term has an s plus 2 squared, and of course the s plus 2 in the denominator is going to wipe out that square, but we're still going to be left with an s plus 2 in the numerator. So we're going to have an s plus 2 squared term in the numerator and s plus 2 in the numerator over here. Setting s is equal to negative 2 is going to wipe both of these out. So s is equal to negative 2, the numerator of this is going to be 0, and this is going to be 0. We're left with just a k2 on this side of the equation. So then we have to evaluate this side of the equation at s is equal to negative 2. So that's going to wipe out, it's going to wipe out this term over here, and we're going to be left with 2 divided by s plus 1, where s is negative 2. So this is going to be 2 divided by negative 1, so we're going to have k2 equals negative 2. Again, it's looking a lot like the last problem. That is just purely coincidental. Well, it's not entirely coincidental. We're using about the simplest equations we can to do this process. Okay, so the last part is what's tricky. The last part is solving for k3. So if we were doing our normal approach we've done so far, solving for k3, what's going to happen here? If we were doing our normal approach where we just multiply both sides by s plus 2, the problem in this case is if we multiply both sides by s plus 2, that's not going to wipe out this k2 term. So if we multiply both sides by s plus 2, we're going to be left with an s plus, we're going to have k3 plus k2 over s plus 2. So it's not going to get rid of that term. So there's different techniques for doing this. The standard approach to doing this is we're going to differentiate both sides of this expression with respect to s. So what we're going to do is, and actually we're going to use, we're going to use the form we had previously. So we're going to use the, So we're going to differentiate, we're going to go back to our previous expression here, where we had K1, sorry, I shouldn't have deleted this. So we're going to go back to this expression we had here, where these guys canceled, and we canceled one of those out. And we're going to go back here, and we are going to differentiate this with respect to s. So we're going to take the derivative of both sides of this expression with respect to s. So the left side of this expression, the derivative of 2 over s plus 1 as a function of s is going to be negative 2 over s plus 1. Sorry. Yeah. So if it makes more sense to you to write this as 2 times s plus 1 to the negative 1, and it makes more sense for you to do the derivative that way, you can do it. Or I can write it this way. It looks like in my notes I had it written wrong. And this is going to equal k1 times, so for the k1 term, we have 2 functions of s here. So if you take the derivative of the product of 2 functions of what you're taking the derivative of, you have to do one function times the derivative of the other plus the derivative of one function times the other. So you got to do, I forget the name of that one, but you got to do that process. And we get 2 s plus 2 divided by s plus 1 plus negative s plus 2 squared divided by s plus 1 squared. And then lastly over here, what's the derivative of this? It's just going to be k3. Okay. So now, how can we find this value of, how can we solve for K3 here is what we're trying to do. Well, to solve for K3, we can just choose a value of s that's going to wipe out this K1 term. So if we choose s is equal to negative 2, right? S is equal to negative 2 should wipe this out, and we will have negative 2 divided by negative 2 plus 1 squared, so that's going to be negative 2. Oops, that's not right. Yeah, right. So we're going to have, so negative, so we chose it, negative 2. So we have, this term becomes a negative 1 squared, which is a 1, so we have negative 2 over 1. We have K3 equals negative 2. Okay. Okay, and I'm not going to expand that out. So, well, I will expand that out. So our function then, our function of s is going to be 2 over s plus 1 plus negative 2 over s plus 2 squared plus negative 2 over s plus 2. And if we want to write that as a function of time, We want to take the inverse Laplace of that. We can just write that as, the only thing that's kind of tricky is the repeated root in the denominator. That's just gonna, this term is just gonna be -2, and because it's squared, it's gonna be t times e to the -2t. So our overall expression, f of t, is gonna be 2e to the -t plus -2t e to the -2t plus -2e to the -2t. Okay. So the last type, and let me just take a pause. I heard a sound come from the camera, so let me just check this really quick. Yep, we're still good. All right, we're still good. The last type is going to be complex roots. So our example is going to be s equals to 3 divided by s times s squared plus 2s plus 5. Okay, so how do we choose the... So again, we're going to pick a general form for this solution. We're going to assume the solution can take a general form. So in this case, we're going to pick... we have our s is equal to 0 root here. So we're going to have k1 over s. And now for our complex roots, we're going to have to choose a numerator that has an equation with coefficients in front of s's with an s order that is one order lower order than our equation here. So in this case, we have a second order equation of s, second order polynomial as a function of s, which means our numerator is going to have to be a first order function of s with each ordered s term having a different coefficient. So in this case, we're going to have k2s plus k3 divided by s squared plus 2s plus 5. So that's going to be our assumed form of the solution. Okay, so how do we solve this? Well, again, k1 we can solve fairly easily. So k1 we're going to do it just using the normal approach. So in that case, we're going to multiply both sides of this equation by an s. So we're going to multiply this side by an s, this side by an s, this side by an s. That's going to wipe out the s here. We're going to pick s is equal to 0 over here. So we're going to pick s is equal to 0 to completely wipe this guy out. So all that's left, when s is equal to 0, all that's left on this side of the equation is k1. Over here, these s's cancel each other out. S is equal to 0, so we have 3 divided by 0 plus 0 plus 5. So k1 in this case is going to be 3/5. Okay. So the question now is, how do we find k2 and k3? So the solution to how do we find k2 and k3 is to, we are going to take this expression and multiply it by its least common denominator, or lowest common denominator. I can't remember. Anyway. So we are going to, so in this case, we're going to multiply both sides of this equation by by this denominator here. So when we do that, when we multiply both sides of this equation by that, we're going to get 3 equals, when we multiply this term by this expression, the s's are going to cancel, so we're going to be left with, and sorry, these s's do not exist anymore. So we're going to be left with k1 times s squared plus 2s plus 5. And then over here, we're going to be left with, multiplying by this, we're going to get, this is going to cancel out, we're going to be left with an s in the numerator, so we're going to get k2s squared plus k3s is going to be our last remaining term here. Okay, so now we can, we're going to rearrange this in terms of coefficients of s squared, coefficients of s, and then just constants, coefficients of s to the 0, I guess. So we're going to be 3 is equal to, so we have